Bismillahirrahmanirrahim. In today's video, I will solve a 2k fractional factorial design in which we have 8 factors that are represented by a to h. We have a blocking factor engine that is represented by 1 and 2. Half of the observation or treatments have been carried out on engine 1 and half of them on the engine 2. We have only one response variable that has been represented by co and s. So step 1, we have to make a factorial design. Click on stat, then DOE, then factorial, create a factorial design in which we have 2-level factorial with default generator, the first option. Then we have to select the number of the factors. We have 8 factors. Then click on design. In the design, we are working on 1 divided by 16 fraction. We have only 16 run. If we have a full design with 2 levels and 8 factor, we have to perform 256 experiments. But in our case, we have only 16 experiments. So it's a fractional factorial design of the resolution 4. About the resolution 4, so the information regarding the generator is available on the page number 7 to 9 of your book Design and Analysis of Experiments by Montgomery. Here you can see that the main effect A, B, C, D, E till H, they are aliased with the 3-level interaction. However, in a resolution 4 design, the two-way or 2-level interaction, the 2-way or 2-factor interactions are aliased with each other. Understand it that 2-factor interactions will be aliased with each other and main factor effect will be aliased with the 3-way interaction. So now we have number of blocks. There are 2. Click here, select 2. Nothing else to do. Click OK. Then go to the factors. You can see the factor names are listed by A till H, and the low level of the factor is represented by -1, whereas high level is represented by +1. Click OK. Then go to options. Please must uncheck this randomize run because it will help you in entering the data. Click OK and then click OK. You will get a design. Now the next step is entering the value of the response variable. So right here co and s, then you can enter the values similarly like in the Excel, like 1, 3, 7, 6 or 7, like this. To save the time, I have entered all of the values. Now we go towards the analysis. Again go to stat, then go to DOE, factorial, analyze factorial design. Here select the response, click on once and then click on graph and then select 4-in-1 as well as half normal plot. You can uncheck this preto. Click OK and then nothing else to do for the first. Click OK. To view only the results, click here, output only. You can see we haven't got our model summary, neither we got our ANOVA results. If we come down, we haven't got our residual plots. So why? What's the reason? The reason is because there is 0 degree of freedom associated with the error term. This error term is used in the computation of MS error, mean square error, and if we haven't mean square error, we are unable to find our f value, and based upon our f value we calculate our p value. Now what's the solution? We have to drop insignificant terms, these terms either main effect or 2-way interaction from this model, and those terms will be pulled out to the error term. In this way we will get our error term and thus we will be able to find f and p values. Now what's the way? The easiest one is to use the half normal plot, this one. You can see in this plot those terms that have a significant effect, they are represented by the red color boxes. However, those terms that are not significant, they are represented by a blue color dots. We have to focus on these red color square boxes and we have to retain only these terms in our model. Rest of all of the term will be pulled out as a error term. So we can see it here that B, C, D and E, these 4 main effects are significant, whereas in the 2-way interaction terms AG and AH are significant. However, the main effect of G and H, whereas A, G and H is missing as a main effect, but we will have to enter it. Why? Because its high level or its 2-way interaction terms are significant. So entering a 2-way interaction term without having the main effect term is impossible or is not allowed, or we can't do it. So in short, we have to enter A, B, C, D, E, G and H, these main effects. So let's go to stat, then DOE, then factorial, analyze factorial design. This time click on the term, move all of these terms on the left hand side by clicking on this double arrow towards the left, then enter the main effect. So A, B, now C, D, E, not F, G, H, and now two interaction terms we have to enter GH and this AG, and then we move AH there. After that we will be able to perform the analysis again, AH and move it there, so that we have our model terms that we want to retain in our model. Click OK. Go to the results. Please select the expanded table. Usually by default simple tables has been selected. Click on expanded tables, then click OK. After that click OK. So you got our results. Click here to view output only, slightly maximize to view the results. First of all, come down and look for the residual plots, because these are the assumptions of the ANOVA. Before going towards the result interpretation, you have to first check that whether assumptions are met or not. So this first and third plot is telling us that the data is following normal distribution. No, there are no significant outlier in the data, hence the normality assumption has been satisfied. This graph number 2, it is telling us that the negative residuals that lie under this dashed line and the positive residuals that lie above this dashed line, they are somehow equal in number. So it means that the variance of the data is almost constant. This graph number 4, it is telling that there is no cyclic pattern, no 6 or 7 point above the central dashed line, means the zero residual line, and there is no repetitive patterns have been found. So the data is found to be independent, and thus all of the assumptions have been satisfied. Click OK. Now go above and we have to first look at the model summary. The model summary is depicting that 99.70% variation in the model has been explained by the term that we have included in our model, and those terms are A, B, C, D, E, G, H, and the interaction of A, G and AH. So this was the explanation of this model summary. After that we have to look at the ANOVA table. ANOVA table depicts first of all the blocks. The blocking effect has a p-value less than 0.05, so it means that the effect of the blocking is found to be significant. Then we look at the effect of linear terms. So we can see it here, the p-value associated with this term A and the term G and H, they have the p-value greater than 0.05, thus they are insignificant terms. However, the rest of them all are 0, 0, have a p-value of 0. It means they are very much significant. If we talk about two-way interaction, both of the two-way interaction has the p-value less than 0.05, so they are also found to be significant. Now, how we can rank them their significance? We can rank them based upon their percentage contribution. The percentage contribution, you can see it here, the highest percentage contribution is of parameter or variable E, that is 39.44, followed by the parameter C, 16.16, followed by the contribution of AH, that is 21.21%, and then on the third number the percentage contribution of the parameter C, that is 16.61. So in this way you can identify the parameters, or you can identify the parameter of terms in the descending order of their percentage contribution. How we can calculate this percentage contribution? For example, if you want to find the percentage contribution of C, so use the sum of square SS term, that is 0.28143 divided by the total sum of square, that is 1.69456, and you will get this value of 16.61. After the ANOVA table, we will go towards the regression equation. In the regression equation, this first term is the constant, and after that there is a coefficient associated with all of the terms that we have considered on our model. The terms that have a negative sign, you can see they have a negative effect on the response variable C, O and S, where so it means that with the increase in those terms, for example, with the increase in A, there will be a decrease in the CONS. How much? So you can write it like this, that with the increase in 1 unit in A, there will be a decrease of 0.00537 units in the CONS. For example, one more, that with the increase in 1 unit of E, there will be a decrease of 0.20438 units in the response variable CONS. Now we have to find the graphs. So in the graph, for the graph, we will go again to the stat, then DOE, then factorial. Here you can see these are the factorial plots. Click on them and then select those terms that have been included in the model, in the refined model. So we can remove F from here because we haven't included F on our model. However, if you retain, you can click OK and you will get your main effect plot. So how you will interpret them? So initially you will say that with the increase in B from low level to high level, likewise with in B, C, D and E, with the increase from low level to high level, there is a significant increase in the value of the response variable. That's why the graph is going up. For the factor A, with the increase in the level of the parameter A from low to high, there will be a very insignificant or minute decrease in the response variable. Further, there is no effect further for the parameter G and H. Moving from low level of the parameter to high level, there is no effect on the response variable. How so? These are the most insignificant terms in the model. Now we have to create an interaction effect plot. So for the interaction effect, I suggest to people to make only those interaction effect plots that are significant. For example, you can see it here that only A, G and H are found to be significant. So draw only those graphs. In order to draw those graphs, click on stat, then ANOVA, here interaction plot. In the interaction plot, select AG. So here is the A and G. Please select only two variables at a time in order to get a good graph. Then click OK. And so you got a graph between A and G, and you can see it here that both of the lines are intersecting each other, so depicting that there is a very strong interaction between these two terms. Likewise, you can do it for A and H. Also make contour plot. How? Go to stat, then go to DOE, factorial. Here click on contour plot. In the contour plot, select your response CONS, then select on the x-axis we need A variable, A parameter, on the y-axis B. Click OK and we will get our contour plot. How we can interpret it? So based upon, first of all, focus on these values, that the dark greenish area shows that CONS value, response value is greater than 0.80. So in case if we want to maximize our response variable, so we will select the high level of the parameter B, because at high level you can see there's a dark greenish area where our response variable is maximizing. And now what about the parameter A setting? So whether the parameter A is at low level or it is at high level, you can achieve the highest level of the response variable. In case we want to minimize our response variable CONS, so there is a region where light greenish color and the response variable value will be less than 0.6. So you will have to select low level of the parameter B that has been represented by -1, and there is also no effect of the parameter of the factor A on the response variable, because at low and high level you are getting the least value of the response variable. In order to identify the settings of your parameter in such a way to maximize or minimize your response variable, you can do it with the help of response optimizer. Go to stat, then DOE, then Factorial, select the last option, response optimizer. In the response optimizer, first of all, select your goal. Our goal is to maximize our response variable. You can minimize it, you can set it at a target. Then click on setup. We have nothing to do here. Then click on options, all okay. Then click on graph. We need our optimization plot. This is the most important thing we need. Go to the results. Okay, parameter solution, yes, it's okay. So nothing else to do. Click OK, and then we are waiting for our response optimizer. So you can see it here. The solution is we have to keep our factor A or parameter A at low level, while B, C, D, E, G at high level, and the parameter H at low level. And we are getting a desirability value of 1. This value, the desirability value, is maximum at 1, and those values that are above 0.85 or 0.9, they seem to be quite good. Now this is the graph of the response optimizer. So you can see it here. We have, in order to maximize our response variable, we have to select, this is the low level and this is the high level of the parameter. So we are going to select low level of parameter A, high level of B, high level of C, D, E, G, and low level of, in order to maximize our response variable CONS with a desirability value of 1.00.